Yeah. Yeah, so that's a fabrication issue. We could do that, but we haven't explored.
What is the long-term stability? Suppose you implant some of these threads under the skin for pressure sensing. What will be the stability and the long-term robustness?
Anything that deals with chemical, not stable over long term, that senses. Anything that does physical measurements, like temperature, pressure, can be engineered to, we haven't studied for how long, but can be engineered because they are just basically conductive threads that change their resistance every time you touch them, so they're physically they're more reliable when implanted. But if you're monitoring chemical activity with some kind of enzyme, that's not going to stay long for a long time. So I think the strain sensor, force sensor can be sort of sutured or implanted just underneath the skin, right, for example. And I mean, I can't give a number, but I don't see a problem where we can't make it work for a long time.
So is like sterility a concern? Because if you're implanting skin,
very good question.
how do you
Yeah, very good question. So the suture work that we did, if you notice, the picture showed just the wicking inside. So when we got the approval to do any of these studies, they didn't let us put the sensor directly right in there. And that is a medical grade suture. That's a medical grade suture, so that will work, and it's FDA approved. But if you're doing sensors, you can only use it if the materials are biocompatible. So not all the sensors would work, but some of the sensors work. Yep. Sorry, I'm sorry. I took more time. Yeah, no, I understand. I'm gonna get out of your way in a minute.
Hi.
In your office hours, can we also ask you questions about like the coding assignment? Or like you're too important or royal to...
Oh,
I did like the binary bag of words, the count bag of words, the TDF, TF-IDF. I did the theory part of the homework, but I don't understand how we actually use the information we have to do probabilities for the naive Bayes for the coding part. Like, where do we get the probability of a document belonging to any one of the 20 that we have? Like, is it the total frequency of? I mean, where does the probability
So
come
let's
from?
ask this now. I mean, I'm going to go back to naive Bayes. And I think it will be, it should be clear, I hope.
Because even I did the theory part and I did that naive Bayes, but then like when I did the coding one, I was like, I don't know. Where's the probability?
Okay. Sorry about it. We got 2 screens. That's the gain of having a lecture before. We lost 5 minutes and had to restart this because there was something, I'm not sure what, but anyhow. So this is where we are. And what I want to do today is I want to finish understanding what naive Bayes is, maybe why it works also, and then move on to generalizing naive Bayes to a more to an interesting setting of, let's call it semi-supervised learning or unsupervised learning. But let's first finish where we left off, or start where we left off last time. We talked about naive Bayes. So naive Bayes is a probabilistic algorithm that makes a specific assumption on the conditional independence of the features. And because due to this assumption, the estimation, the probability of this feature vector that we have here, P of x1 equal b1, x2 being b2, xn being bn, can be decomposed as this product here of just P of xi given bi equal to bi given v equal bj. So we don't need to look at all the features at the same time, but rather each one independently. So a good way to think about it is, again, as a generative model, similar to the way we thought about documents last time. So you first generate the label, the v, according to some probability distribution P of v that you see here. Once you have a value for v, let's say it's vj, you generate independently each one of the features according to P of xk given vj. And therefore, the probability of the example, given that the label is vj, is just this product. Okay. And so what we said is that this learning method basically requires us to estimate some parameters independently. Number of v plus n times number of v parameters. You should be able to explain to yourself why this is. And we also said that this is very different than the learning we talked about before. It's really learning without search. We just look at the data. We have a table of rows and one column, which is the labels, and we just compute something. It's not error-driven. And of course, the question is, why would that work? And again, this is an important thing to think about. And really, the assumption is that of conditional independence, which I said is going to be explained in these slides. I didn't go over this. We ran through an example, and it's a simple example, but you should be able to understand what we are doing here. And specifically, at the end of last time, I got a question that is a very good question, and hopefully all of you know the answer, even though the question should have been asked during class. Basically, the question was, first, let's say we talk about the probability of temperature, or let's say the probability of outlook, given sunny, overcast, or raining, given that the label play tennis is yes or no. So we said that there are 6 numbers here. Everyone agrees that there are 6 numbers? And that the 4 of them are independent. Other 2 depend on them. So what I really need to compute here is 4 numbers. And the other 2 are okay, are dictated by them. Everyone is fine with this? Any question on this? Yeah.
So then that means with the humidity higher, or whatever, then out of those 4 numbers, only 2 you need to compute, and the other 2 will be...
You're asking about the third row, temperature equal high, mild, cool?
No,
this one.
The one we just looked at, it
Okay, humidity equal high or normal. Okay, so let's see. So given, let's say given yes. So there are two numbers, right? High given yes, normal given yes, but one of them is 1 minus the other, given the yes. Now, the numbers given the no are completely independent of the number given the yes. Again, they sum to 1, so if you estimate one of them, the other one should be 1 minus it. Okay? So that's what you do when you learn naive Bayes. You basically compute these numbers, and specifically, we did it in this example. And really, that's what we are doing, right? So for each one of the V's, in this case, I have two V's. Yes, it's the left column here. No is the right column here. And then I get this product, and I compare them. Now, you had the question of where are the probabilities? What are the probabilities? Is that, can you ask the question in this context?
Yes. What are the probabilities? So what's the question?
So I think you asked the question, what's the probability that the label is yes?
Yes. So that's the prior, right? Like what we see there, the 9 over 14.
That's the prior probability from the data. This is, I get this only by, this is devoted of any example. The probability that the label is yes is 0.64. But once I give you an example, like this one, then the probability of playing yes becomes something else. It becomes this one, in fact, normalized. If you want to know the probability of no given the instance, is this number normalized? The probability of yes given the instance is just 1 minus this. So there are two probabilities of yes, or let's say no here. One is the probability of no just from the data, absent any data. And the second one is the probability of no given this data. Okay? And again, what you get from naive Bayes is just a prediction. These are not probabilities because I dropped the denominator, but I can make them probabilities. Questions on this? Okay, so that's naive Bayes. One important comment here is about the estimation of the probabilities. So we agreed how we get this 2 over 9. It's basically counting how many examples have the value of the feature outlook equals sunny, and the label is yes. All right, so that's how we got these 2 nines. Now, we commented that in general, what's written here is basically what I just said. How many times you have the value of xi being 1 in examples that are labeled v, divided by the number of v-labeled examples. And this sometimes is not going to give me the right numbers, either because n is very small, the denominator, or because ni is 0. It just so happens that I've never seen xi equal 1 in any v-labeled examples. And what we want to do is we want to do smoothing, and this is where we ended last time. So what we gave here is one method of smoothing out of many. It's called Laplace smoothing. And essentially, rather than doing nk over n, I'm adding something small to the denominator and something small to the numerator. In this case, I'm doing it in a uniform way. So my m here is the number of labels, and my p here is 1 over the number of labels. I'm assuming uniform. Now, you don't have to assume uniform. You can say that for some label, the probability is 1/2, and for some of them it's 1/3, and so on. But this is one, you can also assume that everything is uniform. In the case of binary classifier, what you get is this. nk plus 1 divided by n plus 2. And this is the type of smoothing that you're going to do also in your homework. And again, try it without smoothing, see what happens. try it with smoothing, but hopefully it's clear what is the need. Okay, so this is one important computational issue when we deal with naive Bayes or with probabilistic estimations in general. We have to smooth. A second one is that we have to work in the log space. I commented on this last time for numerical reasons. When you multiply a lot of small numbers, you're going to get 0 very quickly. Work in the log space, that's going to save you from it. Questions so far? Okay, so we asked the question of why do things work? And the answer that we gave last time is, well, we made an assumption. We made a conditional independence assumptions. If features are conditionally independent on the label, that is, you see the label is yes, and given that, the value of x1 is independent of x2, is independent of x3, and so on. If you believe this assumption, this is the optimal thing you can do, right? We computed the most likely label. In real life, it's never the case, and you can ask yourself, why does it work? It's actually a good classifier, very simple classifier, very good and robust classifier. So we're going to try to explain this in the next few slides. At the same time, we're going to address a question someone asked on Piazza. Actually, we're not learning a classifier, I think. This is how I understood the question. We are just learning how to predict on a given example. Do you agree? That's what we did, right? I told you, look here, how to predict, whether to say no on this instance. I did not give you a function. So is naive Bayes actually computing a function, or is just a method to predict given one example? And that's a very good question, and let's try to address it. So what is naive Bayes doing? Let's take the case of two labels. So V is going to be 0 and 1 for the next few slides. Notice that we're going to predict V equal 1 if this ratio is going to be greater than 1. Right? So this ratio is, this is the probability of 1 divided by the probability of 0. If the ratio is greater than 1, I'm going to predict 1. Everyone is fine? Let's rewrite this. So I'm going to denote here Pi to be the probability of xi being 1 given that V is 1, and Qi is the probability that it's 1 given that V is 0. Remember, I'm going to carry this with me. And now I'm going to rewrite this in a slightly different way. Similar trick to what I used last time. So I'm keeping here the priors, P of Vi being 1 divided by P of V 0. It's this. What am I saying here? So really what's written here is Pi to the xi times 1 minus Pi to the 1 minus xi. Let's think about xi is being 1. If xi is 1, what's written here is Pi, and what's written here is 1. So you can think that it's not written here. Similarly, if xi is 0, what's written here is 1, and what's written here is 1 minus Pi, and that's what you want. Okay? So it's just another way of writing exactly this. Okay, I'm copying it to here. Look at it and try to understand what's written here, because pretty soon the slide is going to be even more loaded. So here I just copied what I've written before. Remember, this is the ratio that satisfies this. If this ratio is greater than 1, I'm going to predict 1. It's just what I carried from the previous slide. Now I'm taking this ratio and writing it in the following way. Essentially, I'm taking from here, out of the parentheses, 1 minus Pi. Okay, 1 minus Pi is out of the parentheses. What am I left with? So I had Pi to the xi, and it's still here, Pi to the xi. and I had 1 minus pi to the 1 minus xi, but I took 1 minus pi outside, so now I'm left with 1 minus pi to the minus xi. Okay? So you should convince yourself that this is exactly this. And the same thing happens in the denominator. Okay? Everyone agrees? Now I'm going to, again, rewrite it. Again, I'm carrying this ratio, and I'm saying I'm going to predict v equal 1 if and only if this ratio is greater than 1, taking log of this ratio. What happens when I'm taking log? I'm getting the log of this ratio from here, the log of this, plus the log of this ratio, 1 minus pi from here, 1 minus qi from here, plus the log of this ratio. Right? I have products, I take log, it's the sum of the logs. Now I'm going to rewrite the log of this ratio. This is something to some power. Log of this is xi log of this. So I get here xi's log of p over 1 minus p, minus, because it's in the denominator, again, xi is outside, log of qi, 1 minus qi. Okay? So what I did is I took the ratio at the top, and I said, I'm going to predict 1 if and only if this ratio is greater than 1. Equivalently, when I take logarithm, I'm going to predict 1 if and only if the log of this is positive. Okay? Now what do I get here? So now I got a function. If it's positive, I'm going to predict 1. Otherwise, I'm going to predict 0. Look at this function and tell me what you see here. So what is it? I have some constant here, right? I have some constant here. What is this part? What is this function? Can you describe it in words? Okay, why? I'm summing over all i's. What do I have here? Some numbers. What do I have here? So what kind of function is it? If you had to give it a name, one word, what is this function? Linear function. Is it a linear function? Who votes that it's a linear function? Who votes that it's a quadratic function? Give me any other option. Exponential function. It's a linear function, right? It's a linear function of the xi's, right? I have a linear sum here, a number, call it wi, times xi. And these are just numbers. They're constant. They do not depend on x, on the instance. So what did I get? What I got was, we predict v equal 1 if and only if this linear function is positive. Right? So again, these are constants. I don't care about it now. So what I got is a function with some w's. These are the w's inside the parentheses here. I'm going to call this wi. So basically, what I got that I can write this ratio, P of vi equal 1 given x divided by P of v equals 0 given x as a linear function. And I'm making a decision, predict 1 if and only if the linear function is positive. Okay, so we're back to talking about linear functions that we did weeks ago. Everyone understand what I'm doing here? So what we showed is that actually there is a function behind the naive Bayes. It's not just predicting for a given example, and the function is a linear function in terms of the xi's. And we also gave a way to compute the coefficients directly by counting, right? Because these wi's are functions of the pi's and the qi's, which are these conditional probabilities. I can actually write it in a more interesting way, yes?
Is naive Bayes always linear?
Is?
Naive Bayes always linear?
What did we show now? I mean, so we started with this, right? We predict 1 if and only if this ratio is greater than 1. And then we did some algebra. We just rewrote this. And we said we predict 1 if and only if this function is positive. This linear function is positive.
No matter what distribution you choose. Like...
It doesn't matter. I mean, this is just algebra, right? So naive Bayes makes the decision based on a linear function in terms in the space of the xi's. That's it. Yes?
How does the decision boundary of naive Bayes compare to something like
Okay, excellent question. So I'll say something about it. But first of all, I convince you that it's a linear function. So it's not more expressive than perceptron or SVM. Is it less expressive, you're asking? The answer is going to be yes, but we're going to get to it in a second. But first of all, I want to write it. So I convince you that I can write it this way. I'm going to write it in an even more interesting way. I'm talking about Boolean classifier. So P of vi being 1 given x is 1 minus P of v being 0 given x. And from that, I can actually write that the probability of v being 1 given x can also be written as this, 1 over 1 plus e to the minus this linear function. Why is that? There's a little bit of algebra here that I did on the side. You have to look at it and convince yourself. Basically, I denoted this guy by capital A, this guy by capital B, and therefore this ratio you can think about, this is log of A over B, which is minus log B over A. I call this minus C. If you do a little bit of algebra, you get that A, which is this guy, can be written as 1 over 1 plus e to the minus the linear function, which is something that we called logistics, or sigmoid, before. So basically, in the case of naive Bayes with two classes, we showed now that the probability of the label being 1, given the instance, can be written using this logistic function. So basically, we're going back to what we've done earlier, and also the linearity of naive Bayes gives a better explanation of why it works. The explanation of last time, which is, well, believe the conditional independence, isn't convincing to me, because in most cases it's not. This is going to be a lot more convincing. So what is the explanation? Back to learning theory. Probabilistic predictions are done via linear models. That's what we showed now. We did it for naive Bayes. In fact, you can do it in a more general way for other more expressive probabilistic models. And the low expressivity now explains everything that, as we did before. It explains the robustness. It explains the generalization. How does it explain it? So really there are two components. One of them is methodology. Is there any reason to believe that when we take data and we compute the fractions that we've done for naive Bayes, we're going to minimize the empirical error? Probably not, right? Why would it minimize the empirical error the way perceptron or SVM that are error-driven are doing it? But really, in general, it's not going to happen, but the way people are going to use naive Bayes is they're going to look at the empirical error. Unlike what I said before, you don't need to look at anything. You just take the data, do the computation, boom, you got a classifier. In real life, and that's what you're doing now in your problem set, you actually look at how well am I doing on the training data? Am I doing well or not? If you're not doing well, what would you do? Assume that you are working in a bank and you're asked to compute this naive Bayes on the data, and you get not so good results with your naive Bayes. What would you do? Suggestions. What did we do earlier in the semester when we looked at the classifier and we said the empirical error is too high? What does that mean on the classifier? Yes? No, you did the weights as best as you could. Okay? What do you mean you overfit? The empirical error is bad. You got 51% empirical error. You're not happy with it. You underfit. What does that mean? You need a more complex model. The model that you're using is not expressive enough. Go back to the beginning, to the middle of the semester, right? We said if we are not getting good empirical error, good performance on the training data, it means that we are not expressive enough. We need to use another class of functions. But we are staying with this. We're going to use naive Bayes. So what would you do if you look at your data, you compute the naive Bayes classifier from it, and you don't do well on your training data? Yes? Add more features. That's what we're doing, right? So that's the learning game, right? You add more features. It means that, given the features that I've extracted, I cannot express the data well. I need to add more expressivity, add more features. So what does it mean in the case of your documents, for example, right? So we gave you bag of words. We ask you to use features that are bag of words. If you were to add more features, what would you do? Okay, take into account the position. That's one way, yes. What does it mean, quadratic space? Conjunctions of words, basically. Rather than this is a word, this is a word, this is a word, you look at pairs of consecutive words, for example. This is more expressive, right? For example, you can take phrases into account this way. You can take negations better into account this way. You can take into account a lot of things. It's more expressive. You're going to have more features if you look at all the conjunctions, or if you look at the positions in addition. Basically, you're going to keep the same classifier, but you're going to use more features, more expressive features. But this is the same game we played at the beginning of the semester when we moved from the straight line to the plane, right? From x to x squared, one example. Or when we just added conjunctions. It's the same game. And this is what's going to happen also in naive Bayes. What numbers do you get on empirical error now in your homework 4? Give me a number. Someone that ran it already. No one? Did you get 90s? Okay, you probably will see 60s or something like that, maybe 70s. Not good enough. Now, we didn't ask you to do this, but in principle, you could add more expressivity. So methodologically, even though the naive Bayes theory says what you're doing is the best thing possible, because under the condition independence assumption, take the data, do the computation, boom, you have a classifier, go home. It's the optimal thing. In real life, it's not the optimal thing, and what people will do is they will add more features. Now, think about it. If the original features were not conditionally independent on the label, of course, when you add conjunction, they will not be conditionally independent. Right? Think about it. If x1 and x2 were not conditionally independent, now when you have x1 and x3, x2 and x3, as conjunctions, of course it's not going to be independent given the label. So we are actually breaking the hypothesis, the assumption even more, but we are more expressive. Empirical error is going to go down. It's a linear classifier. Learning theory told us if the empirical error goes down and you have a low expressivity classifier, it's still linear, you're going to do better. The generalization is going to be better. Yes?
But if you do conjunctions and then the conditional independence is broken, then is that still naive Bayes, or is that some other type of?
It's naive Bayes because the way I computed my weights is naive Bayes, right? I ran the naive Bayes algorithm. I don't believe the assumption that allowed me to derive this algorithm. But it's still, it gives me an algorithm, and I'm following the algorithm. So in the new feature space, I'm still computing P of xi given V for all the new xi's that I have, and then I multiply them, and I have a prediction. So I'm running the same algorithm only on a new feature space. Yeah.
Well, augmenting the input is something you can always do regardless of the algorithm. So if naive Bayes is less expressive than, say, SVM, what are situations where you want to use naive Bayes?
Okay. Excellent question. So first of all, we still didn't say that it's less expressive. It's the next bullet is going to say it. But let me get to it in a second. When do I want to use what? So first of all, the methodology is such that I really appeal to learning theory from a few weeks ago, and that's why it works. Now, there's another question here. Why does naive Bayes actually work in practice? There is a more subtle explanation that I'm not going to get into that has to do with the fact that we are dealing with product distributions, right? So if you look at the way we've written it here, here is good. The distribution really is a product distribution, product of the conditional distribution P of xi given V. And these product distributions are actually very dense in the space of all distributions. By dense, I mean, for the two of you that have seen this, it's a well-defined mathematical terms. It says that next to each distribution, you can find a product distribution. There's a lot of product distributions there, and that actually gives naive Bayes power. We're not going to try to justify it. And B here says, answering to your question, naive Bayes is a linear classifier, but there are linear classifiers that cannot be expressed by naive Bayes. What do I mean by that? Naive Bayes, the coefficients of naive Bayes are essentially fractions of observations, of numbers of observations that I've seen in the data. I can show you a linear function along with the data that is consistent with this linear function, such that if you take this data, you will run SVM, you will get this linear function because it's the best linear function. But you will run on the same data naive Bayes, you will not get back this linear function. So naive Bayes is not expressive enough. It has some advantages. We're going to get back to this point in a few minutes again. It has an advantage that it converges to whatever it can express very quickly, much faster than other linear classifiers, but it does not express everything other linear classifiers can express. You know, if you think about SVM and perceptron, if you give it enough data, they can express anything. Naive Bayes cannot. Okay, so this was just serving to convince you that actually there is a reason it works, and the reason it works goes back to learning theory and linear classifiers that we talked about earlier. But this brings also two interesting questions. One easy, one a little bit harder. For us, both of them are going to be easy. So the way I want to ask these questions is this. So if probabilistic hypotheses are really just like linear functions, can I interpret the outcome of linear classifiers that we did earlier as probabilities. Before we just said, well, we get a number from 0 to 1 in the output of SVM or perceptron, but we didn't say it's probability really. Is it, can you make it a probability? The answer is going to be yes, and it's a very simple tweak of tuning. And then you can ask the second complementary question, if probabilistic hypotheses are like linear functions, can I actually train them similarly, discriminatively, error-driven, just like I did SVM and perceptron? Why do I think about it as doing counting or maximum likelihood directly in a simple way we did? And both answers are going to be yes. And I'm giving you two examples. We're going to do the first one, which is the classification one. We're not going to do the HMM one, but every probabilistic model can be trained also discriminatively. So let's address the first one first. This is what we showed first on naive Bayes, right? We showed that we want this ratio over there to be positive. We showed that this ratio can be written as a linear function, and this gave us this logistic function. Now, in general, if you train a classifier F using SVM, perceptron, we know, and you get a number between 0 and 1, this F here, you can also write it in exactly the same way. So the probability, and tune A and B's such that it becomes a probability distribution. There is a very well-defined notion of what does it mean that something behaves like a probability distribution, which I'm not going to get to. But ideally, what you want to say is that if the output of your model is 0.8, then 80% of the time, when it says 1, it's correct. That's a little bit hand-wavy, but basically that's what you want. That's how you want your classifier to behave. You want that the 0.8 that you get is more indicative that it's a positive example than if you get 0.7, right? That's what you mean when you say, I want that the 0, 1 number that I get from my model to be probability, not just a number, right? So you can make it behave this way by tuning these parameters. And several packages are doing it. LB Java for my group is doing it, and a few others are automatically, or if you ask, will tune. And when they output a number between 0 and 1, they'll promise you that it behaves like a probability. Okay, second question, the more interesting question. So we derive an expression using naive Bayes. This was the expression that we derived. We said the probability that I'm writing it now in one line, so the fraction is here. The probability that y is 1, given the instance and the w, is this, 1 plus e to the minus linear function, 1 over this. Now, when we did naive Bayes, the w that we got, the coefficients, we got them through counting. But you can ask the question, why should I do it through counting? Why can't I find the best w given the data? You see that this is not the same thing. Before, when I ran naive Bayes, I promised you it's going to be the best w if you believe the assumptions. Do this computation, and you'll get the best w given the assumption. Now I'm telling you, take the same functional form and ask the question, can you compute the best w given the data? Forget assumptions. Not the same thing, right? Not the same question. And of course, we can do this because we learned gradient descent. Now we can do it with gradient descent. So I'm going to train. Training is going to be more difficult. In naive Bayes, training was trivial. But I'm going to get the best w, so I'm going to be more expressive. And again, you can compare between naive Bayes and this algorithm that I'm presenting now that is called logistic regression. And what you will see that indeed logistic regression is going to be in the limit better because it's more expressive. On the other hand, naive Bayes is going to converge to whatever it can converge much faster than logistic regression will converge to whatever it can converge to. So you're going to get solid results very quickly with naive Bayes, but perhaps not the best results. So what do we do? How do we do it? Basically gradient descent. So we're going to take this and ask the standard optimization question that we asked several times already. Here is my function. My goal is to find the best W, comma, B to maximize the log likelihood of the data. So that's what I'm going to do. I'm going to minimize the sum over all my examples, this function, log of the probability of y is 1 given xw, which I'm just copying this from here, sum over all w, over all examples, 1 to m, of this expression. And this optimization problem is called logistic regression. Sometimes in the NLP community especially, you'll see it also mentioned as maximum entropy. I think this is disappearing with time. Used to be more popular, now less, so let's forget about it and go back to our optimization function. So that's what we want to optimize. Now, we already convinced ourselves earlier in the semester that we not only want to optimize the empirical error, which is this expression here, we want also to add regularization parameter, and we like the regularization parameter to be a function of the size of W. So we're adding this, and that's what we're going to optimize now, okay? And again, we're going to have this C to trade off between how much we care about the empirical error versus how much we care about regularization, and that's it. And now we're going to do gradient descent on this. So we are really back to what we talked about earlier in the semester, right? So we have an expression that is the empirical error. It's our behavior on the data. And we have an expression that has nothing to do with the data, has to do with among all W's with specific behavior, I want to choose the one that is smaller size. So it's exactly the same thing that we've done before, right? So we have a loss function, we have a regularization error. I remind you that we had L1 SVM that also had the same form, right? A regularization term and a loss function here. We also talked about L2 SVM, same thing, regularization and some loss function. And if you look at the graphs, which I put here color-coded, you will see that really it's very similar, right? So the green is the SVM that we used before. The red is the function that I'm talking about now, logistic regression. They look very similar. And not surprisingly, it doesn't matter which one of them you use, basically. They're going to behave about the same. Questions? Yeah. It's about the same. You can see that it's about the same. Essentially, what do? You take this function and you do gradient descent of the green function or of the red function. And you can see that the functions are the same. So the gradient descent is going to be basically the same. And you can take any package like libsvm, for example. And in libsvm, next to SVM, you can choose. You can check whether you're going to use SVM or logistic regression. They are essentially running the same algorithm with slight tweak because the derivatives are somewhat different. And you can compare, and you'll see that you get basically the same results. Okay, so what have we done? We started with naive Bayes. So in the rest of these slides, stack of slides, there are a few more naive Bayes examples. I'm not going to get into it. But if you want, you can look at it and enrich your understanding of naive Bayes. We talked about naive Bayes as an instance of Bayesian learning. So what does it mean? We want to make predictions. In order to make predictions, we make assumptions on the model that generates the data. We use these assumptions along with Bayes' rule in order to make predictions. In this specific case of naive Bayes, in addition to Bayes' rule, we also made a conditional independence assumption. So to estimate the probability of X given V, we decompose X to its features and said, we're going to think about P of Xi given V for all I. And that gave us naive Bayes. And then we said, let's see what really is happening here. And we showed that really naive Bayes is making predictions as a linear function. And if it makes predictions as linear functions, basically it learns a W. Let's see if we can we can learn the same functional form otherwise. One way is the naive Bayes way, which is sort of a direct computation approach. Another way is the optimization way. You want to learn this W? Okay, look at your data, try to find the best W given this data. And that gives us logistic regression. So we went back to something that we've done earlier in the semester, basically discriminative learning, and show that everything is related. Questions? Okay, so let's move on to talking about still naive Bayes. Keep the naive Bayes ahead. What's happening? Okay, just a small detour reminding you. Surveys, I still hope that all of you and your friends will do the surveys. Projects, I talked with many of you, but not all the projects yet, so please come to my office hours, reminding you that there is going to be an exam. Everything is on the website. So take a look, everything is here too, and let's move on. Okay, so the next two slides, I'm just reminding you that you should know a little bit about probability theory. You should know all this, I'm not going to go over it. You should also know what's expectation, very important because I'm going to use it a lot in this slide, but again, I'm assuming that you've seen expectation, you know what it is, you know that it's linear, it's very important. This last property, that if you have two variables, the expectation of the sum is the sum of the expectations. And let's move on. So let's imagine that we want to solve the following problem. I'm going to use naive Bayes now. I'm going to use naive Bayes to solve this problem. It's called propositional phrase attachment. I want to understand what is the meaning of the word with in these two sentences. Buy car with money or buy car with wheel or with a steering wheel. Okay, so you can see that it's a different type of with. In one case, it's buy with money. The with is attached to the verb buy. In the second case, it's car with wheels. The with is attached to the noun, to the car. And I want to build a predictor that takes these sentences, extract features. I have 4 features because I have just 4 words in each sentence, let's say. And I want to learn a predictor that decides attached to the noun, like car with, or attached to the verb, like buy with. That's my binary prediction. Now I have 4 attributes, and I'm going to take all the conjunctions of them. So I'm going to get total 15 features. So this is my binary prediction, right? So I have examples. Examples are x1 up to xn, say x15 here, with one of these 2 labels. and I want to use naive Bayes. A reminder, how do we use naive Bayes? We put the data in two columns because we have two labels. The left one is the noun column, and the right one is the verb column. And I'm computing the prior, P of n and P of v, P of x1 given n, P of x2 given n, and so on, P of x1 given v, and so on. So that's naive Bayes, right? So then when you give me a new example with a question mark as a label, I'm computing P of n given x, which is going up and down with this product. It's not exactly the probability because I don't divide by the denominator, by the denominator. And the same thing here, P of v given x, which is the product of this number. Everyone agrees with that? That's naive Bayes. If you don't agree, that's a good time to ask a question.
So here, v, x is the data.
X is the data, v is one label, n is the other label. V stands for verb here, n stands for noun, or any other name you want to give the labels. Okay, so now let's assume the game I'm going to play, let's assume I saw 10 examples, okay? And these are the numbers that I got. P of n was 0.5, P of v was 0.5, and these are the estimations for some of the features. I don't have enough room, so I put only 4 features here. And I got 4 numbers given n, 4 numbers given v's, and I can make a prediction. Given an example, the example is 1, 0, 0, 0. I'm arguing that that's what I'm going to get for Pn. Look at it. Pn is the top row here, right? So 0.5 is the prior for n. And then it's 1, 0, 0, 0, so it's 0.75, 0.5, 0.5, and 0.5. Really, it's not this 0.5, it's the 1 minus this that I put here, because it's 0, but turned out to be the same value, right? Everyone is with me? So I can make a prediction, the same thing here. This 0.25 I got from here. How did I get this 0.75 here? This is P of x2 being 0 given v. Everyone agrees that it's 0.75? It's the 1 minus this guy. Okay? So that's naive Bayes. And you can see that I'm going to predict n for this example. Okay. Everyone is okay with this? Now assume that in addition to these 10 examples, I'm also giving you 100 examples, but they are unlabeled. Can this help? So now you have a model, right? After you've seen the 10 examples, every new example that I can give you, you know how to predict on it using naive Bayes. Everyone knows how to do this? What about if I give you other examples, but they are not labeled? Can you use it somehow? How about you guys here? What do you think? What do you think? Can I use these examples somehow? Any suggestions? Yeah?
I guess you could predict on those examples and then use those predictions to alter your probabilities.
Okay, suggestions. Good suggestions. What does this mean? What did you really say? Can someone rephrase this? Well, what do you mean by imputing the data?
It's almost like you have like 110 examples and then 100 of them are missing the label.
Right, but no, but Daniel gave us a suggestion. He said, you know how to predict, right? I showed you that I know. I predicted on 1000. So why don't you predict on all these 100 examples? Now they'll be labeled. And now take these 110 labeled examples and run naive Bayes on them. Good idea, bad idea?
But would that really improve the quality? Because like, if anyway, it seems like, I mean, even if you get 110 labels, they're all based on the information from 10 only, you know? So it wouldn't, if you now train the model on 110, would that be really better than the original 10, which has all the information in it?
Okay, good questions, yeah.
What if you don't have enough information from that 10 labels and you predict those 100 and predict them wrong and we have like make them all go in one direction?
So you say it's risky, yes?
Well, at the very least, you'll know that the problem wouldn't be correct if you like predicted it on up to like 100 examples, and it turns out that the prediction makes it such that the ratio of like positive and negative examples is no longer the same as the prior. Then you know that the prior was.
Okay, so basically in the same vein, you're saying, maybe it's wrong what I'm doing, and you suggest a way to figure out whether I'm wrong or not. But in principle, you know, it's a good goal to try to use these 100 examples somehow, right? So here is one suggestion. Can you give me another suggestion for how to use this? Maybe I will not use all these examples. Maybe I can use some of them, yes?
Yeah, as a variation on that, focus on the ones that are most similar to the ones that you have labels for, so you're most confident in your computed labels for them and build out from there.
What do you mean by most similar?
That the probabilities are closest to either 1 or 0 based on the data you have.
Okay, so you're not saying similar, you're saying confident. So for example, here I got 3 over 64 and 3 over 256. So what is the probability? Had I normalized, what would I get? 64 is a fourth of 256, right? Something like that. So what's the probability here to predict n versus v? Someone that can compute fast? 80%. So here, I'm 80% confident that it should be n. Let's assume I have another example that I'm 95%, and another one that I'm only 51% confident.
Can you set a threshold then of confidence and say,
So maybe I can improve Daniel's algorithm and say, you know what? Don't take all the 100 examples. Take only those that you're very confident. Now you know that the labels are good, or you have reasons to believe the labels are good, and your concern that I'm adding noise to the data is less of a concern. So I'm going to just take those that have more than 0.8 confidence, or less than 0.2, right? So I care about the extremes because I'm confident about the extremes. I'm going to take those. That seems like a better, potentially a better way. So let's see. So we're talking about, will that help, right? So we have an estimate for the label. I'm just summarizing what we've said. And we want to try to improve it, to use it to improve the classifier. So we talked about this option, right? So we can make the predictions on all the 100 examples and believe them. This was the original suggestion, but some of you are concerned that maybe it's going to add a lot of noise because a lot of our data now is going to be labeled incorrectly. So we can use some of them. And the suggestion was use the confidence. You can also say, not the confidence, but I'm going to take the top 10%. Okay, so I don't want to put a threshold on the confidence because I don't know what I'm going to get. I'm going to take the top 10 examples in terms of confidence, add them to my label data, and now I have 20 examples. I'm recomputing my naive Bayes model. Now I have a better model, and I'm going to do this again. And I'm going to iterate this way.
So you're saying that you have the 10 examples, then you run it on the 100 you set a threshold. Say you're confident, highly confident of 20. So you label those, and then you train the model on the 30, and then you run it on the 70.
So what I said is that I have two options. I can either threshold at the confidence level, only those that are at least 80% confident, or I can say I'm setting a confidence by number of examples I'm willing to take. I'm going to take the top 10 confident examples. Yes?
So you said we're given an additional 1,000 examples and we want to use them somehow.
Only 100, yes. Yes.
Okay. But if we don't have the labels, then how are those examples more interesting to us than, say, randomly generating a bunch of examples?
Good question. Why? I mean, there are random examples, but there are random examples that come from the same distribution. And moreover, I'm working under the naive Bayes assumptions here, that things are conditionally independent given the label. So these are not all examples, not all bit sequences can appear here. Right? Because some bit sequences do not satisfy this. So it's a good question. So I'm assuming that there is some naive Bayes classifier out there that can classify all this data, only that someone gave me this data, but dropped the labels. Yes?
What is it, once you start doing this stuff, you start guessing with a sample, what does this do to your generalization error, which was a function of the number of examples you had?
Okay, let's get to it next time. So now let's talk algorithmically. So we have an algorithm now, an iterative algorithm, but there's one thing that you were missing, which is, look at this, at what I got here. So what I got here is that this example is 0.8n, but it's also 0.2v. Now, when I'm taking the labels and adding them to my pool of supervised examples, who said that the labels have to be 1 and 0 or n and v? Why can't the label be 0.8n, 0.2v? Think about how you compute naive Bayes. You count how many n examples do you have, how many v examples do you have, how many times xi is on in a v example, how many times it's on in an n example. You can deal with fractions. No one says that this algebra has to be done with integers. So I can improve the suggestion that you've given me, and I'm going to assume that the example 1000 that I gave you before is n labeled with probability Pn divided by the sum, and it's a v example with PV divided by the sum. So it's a 0.8n, 0.2v, and now I'm going to label all the examples. Now, think about it. I'm achieving the same thing as we achieved with the confidence thing. Because if the example is 0.5 confident, I did nothing. It's 0.5n and 0.5v. When I do the counting, it adds the same thing to both sides. If one is 0.9 and 0.1, it adds a lot more to the 0.9 side. So that's what I'm going to do. So I don't have to work with labels. So that's what I'm going to do. So we basically suggested a family of algorithms. These are the algorithms that you will play with at the end of your homework. Use the threshold. Use fractional examples. And that's it. So these are semi-supervised algorithms. We can use them iteratively. And in fact, it's a general scheme. Whenever you have an algorithm, doesn't have to be the naive Bayes. Any algorithm that gives you a confidence in its prediction, you can do this with it. once you have a bunch of examples that are not labeled. The only requirement really is that you have this robust, or you believe, robust confidence measure in the classification. So these are called bootstrapping algorithms, and this is the key family of semi-supervised learning algorithms. There are other families of semi-supervised algorithms that are called graph-based. We're not going to address them. What I want to do is I want to move to another question, which I want you to take home with you. What happens if instead of 10 labeled examples, we start with 0 labeled examples? So I just dropped one character. What would you do then? Yeah?
You need to, I mean, like we were saying before, like having random generic examples and having those 100 labels, not the 10, because we assume there's some distribution from which this 100 examples come from. So then here, you would at least need to make some assumption or have some belief about what is the underlying distribution of the example. So you have no example from that distribution.
I need a distributional assumption. Excellent. Without that, nothing is going to work. I am going to assume the naive-based distributional assumption. And to make this short, I'm going to do the same thing. So what did the 10 example gave me before? They gave me a guess for a model. Probably not a good guess with 10 examples. When I get 0 example, I'm also going to start with a guess and do the same thing. I'm going to guess my model, and I'm going to keep on going under the naive-based assumption. Now, as something to think about, we're going to develop this next time. Think about a coin problem. So I actually have 2 coins here, and I'm going to generate, if I toss this coin 100 times, you look at the head and tail, you can tell me which one, what's the bias of the coin. We agreed on that. If I have 2 coins, and I'm telling you, now I'm tossing coin 1, and now I'm tossing coin 2, you can also do the same thing. You look at the 1, and you'll estimate its bias. You look at the 2, you'll estimate. Now imagine that I have 2 coins, and I'm generating a sequence of tosses, but I'm not telling you which one I used. I used a little bit of 1, a little bit of 2. I mix them. What would you do? So think about this. This is exactly the same problem, as we will see. The solution is you start with a guess. You estimate using this guess, and you correct based on what you see, kind of like what we did with the naive-based algorithm. So think about the coin problem. We're going to continue from this on Monday. Have a good weekend.
I'm totally confused now. How? I mean, my fantasy was that like SVM, for example, like you said, like it was created based on like statistical learning theory, and like you maximize this and that, and such a great model. And like my understanding from other classes before was like SVM has like very good performance in general.
Why is logistic regression as good?
But then I thought, I never saw logistic regression as being as powerful.
Logistic regression.
Why you have both? And if one was created already, then
they're not
created the second one. Then you say, oh, that there's no merit. You just relabeled, rebranded.
No, it's not exactly the same, right? So you see that the loss functions are somewhat different.
Yeah, I mean, but you're the one who defends like, well, I don't know.
It's very similar.
So if you had to, if before you look at the data, which one would you choose?
I would probably use SVM.
Because of the motivation?
It's a little bit better experimentally, but again, it depends on the loss function. These loss functions are not the right things, right?
Yeah.
They are both surrogate losses. They are approximation of what we want to do, and
You mean because of the gradient
experimentally,
descent or because of
no, because really what I want is I want to get all the positive example positive and all the negative example negative, and I don't do this.
Yeah.
What we do is instead we use hinge laws or
And we do the
exponential
soft-
laws,
yeah.
and we do something that is close to what we really want. But
I know-
that's what we have.
That's why I'm confused how like naive Bayes can be linear function, but then it's also logistic, and logistic is not linear, right? Like even that shape, like
What do you mean? What do we mean when we say linear? We mean that the decision boundary is linear, right? So there is a linear function in the space of instance of the xi space, such that positive example are on this side and negative example on that side. Logistic is it's making the decision based on a linear
okay,
function.
because I thought that like for
You take the
linearity
example.
you would have to, because like in logistic regression like things change in the scale of the log of odds, right? So it doesn't change like I cannot just like say multiply by some factor, like it doesn't change linearly, like
No,
the
but-
probability,
but
right?
the
Like it,
decision boundary is linear, right? So you give me an example, you multiply it by a linear function. If it's greater than 0, say, you say yes. If it's greater than 1, if it's less than 0, you say no. So the decision boundary is linear. It's true that the update, the way you update stuff,
It's
when you
not.
learn, is not.
okay. Okay.
I have a question in the homework. My computer died, so it's kind of small. In this equation that we have for in a case that one of the probabilities is going to be 0, so because we are multiplying them all
The
together.
smoothing.
Yeah, the smoothing. Yeah. This v here, or I don't know if it's v. Probably not. It's not v. This
Yes.
is this vocabularies, all the vocabularies in each class, in a specific class, or all the vocabularies of all the documents.
Oh, it's the vocabulary in your dictionary. It's the feature space.
Would be
That's
everything.
how we define it, right?
I mean, when I use v as equal to all the vocabularies in specific class. So when I say, like, you have 20 classes that you're trying to define. You're trying to put it.
Yeah, I think that's the way we define it. Yes.
But like, it doesn't make sense if that's. I don't know why would that be?
Let's assume that all the words appear in all the classes. Right?
But they don't.
Yeah, but that's just a coincidence.
Is it because like we're talking about different topics, right? Some words do not appear in some topics.
Yeah.
So why do we use all the words in all of the topics in the denominator?
Well,
instead of just saying which
so the method
class?
says this, right? So really it doesn't matter. So
The reason I'm saying this is because when you do all of the words on all the classes, in Python, when the number on the numerator is really small compared to the denominator, it's not going to be 0, but it's like very, very small. When you do a log, it assumes it's small, it's 0.
no way.
Yeah. So when I get to the case, like when I put k, so like when I have a value, I print the value of numerator and denominator, and none of them are 0, but one of them is way smaller than the other one, so the value is like very, very, very close to 0.
So can you ask Python to use more bits to compute it?
I don't know.
This is
And
weird.
it's not in the domain of the function. It says it's not in the domain of log, which means it's assuming it's 0, because like the numbers.
So the TAs ran this. And
I guess it depends on what k value you use also, because k value also plays a role. So if you use a high k value, it would happen more often.
But for k, wouldn't like if you take
Because it's k times v, right?
are you using what are you using to represent numbers here? Use doubles or what do you know?
I think it's probably. I'm not sure it's double single. I'm not sure. It might be. It's a float, but I don't know if it's a single or.
If it's float, it's no double. Can you do double?
I may have to do that. Yeah. I don't know.
I'm very surprised. I mean, so you should ask the TA.
The reason
how
I
they
say
ran
this
it.
is because I was doubting my own like math and like the code,
It
but
shouldn't happen.
I print the numerator and denominator before going to the log, and
Yeah,
it's
yeah.
not none of
No,
them
I
is
see
zero.
what you're saying. I mean, but 64 bits is very expressive. You should not get 0 here.
Yeah. What range of values of k should be used? Because like I don't know if k, because I use
I don't
1.100.
remember. I don't remember.
Is it like between 1 or 0 or like what?
I don't remember.
It doesn't matter.
I don't remember.
Because it makes a
really
difference.
don't.
Because if you do 100 times, if you do k as equal.
What did we write in the problem set?
It just said it's a parameter. It doesn't say what range.
We should put it.
Okay, okay.
So,
So I have to look at it. I don't remember, but you should not get numerical problems when you use log space.
yeah, I don't know.
Something is wrong here.
I use math.log, so I don't know if this is the library I'm using. I'm not sure if it's.
What function I base?
I'm using
So who ran it?
the first one, the first name base, like in the code. So the thing is, when the V is really large, so if I use V as of all the words in all, like the dictionary that we
Yeah,
have.
but that's the right way. You should use the whole dictionary. The factor is going to be just 1 to 10 or 1 to 20.
But when I use that, so
So that's nothing, right?
what probability are we expecting? So like I ran it, so just like check if I'm doing it right. I ran it with a specific
Oh,
document.
the probabilities are going to be very tiny.
Or relative probability, like the probability of like, so we have 20 classes, right?
Very tiny.
One larger than the other.
Yeah, but the probabilities are going to be very small. After normalization, even they're going to be small because you have 20 classes.
No, they will be small, but like,
But in the log space, there should not be a problem. So something is wrong here. Either you're using, even float, I thought would be sufficient, but try to move to double and see what happens.
so then I guess I'm not doing it right because like when I run for one specific document in the training, so like I do the training with I know. No, I predicted the class. I predicted the class right. But probabilities that I
I think at this point, probably not, but there's a, oh, totally a major? Yeah. I would guess, no, but that would be a good way to, try to squeeze in an extra. That's an option.